This example problem will do some conversion of units. We'll discuss displacement, distance, position, average speed, average velocity, some basic terms for the physics student to become familiar with. I'm going to apply it to a problem here. We have a person, Sue, that's walking in a straight line towards the east at a speed of 2.5 miles per hour. Sue walks for 0.8 miles and then rests for 2 minutes, stays in place with no motion. She then turns around and walks 0.6 miles in a straight line towards the west at the same rate, 2.5 miles per hour. So this person is moving in a straight line, part of the motion to the east, part of the motion to the west. So let's convert units. We'll calculate average speed and we'll calculate the average velocity. First, the conversion to metric units, 2.5 miles in 1 hour. We can get rid of the miles unit by applying a factor of 1.609 kilometers as 1 mile. The miles units will cancel here. Then to go to meters, 1,000 meters for 1 kilometer, the kilometer units will cancel. And to convert the hours into seconds, 1 hour is 3,600 seconds, so the hour units will cancel. You perhaps want to pause the video and get out your calculator and see if you come up with 1.117 meters per second. I choose to keep 4 digits in intermediate results. This number is going to be used later in another calculation. So I'll round to 3 significant figures at the end of a problem, but for right now we'll keep 4. Now the conversion of the distance, 8.8 miles, 1.609 kilometers per mile again, the miles cancel. Converting to meters, the kilometers units cancel here. And I found 1.287 times 10 to the third meters. My calculator was in scientific mode. If I want to get rid of the 10 to the third, I have to shift 3 places here in the decimal. So 1,287 meters. I'm not going to show the steps, but the same way, 0.6 miles becomes 965.4 meters. So we've converted into more standard units, the metric system for scientific work. Now, what about average speed? Well, for average speed, we need the total distance traveled. Total distance divided by total time. That'll be average speed. We could talk about instantaneous speed. That's not very common, but at one instant in time, we'd have instantaneous speed. But over a finite time interval, we calculate average speed. So we're going to do average speed. What's our distance? Well, these numbers are from the prior slide. 1287 meters towards the east, 965.4 meters back towards the west. What's the total distance travel? Total distance is the sum of all of these. We rest in the middle. That contributes 0 meters, but otherwise distance traveled is not paying attention to plus or minus for east or west. We just add the distances together. So we get 2252.4 meters. Now we need the time to calculate the average speed. We have the total distance. How do we come up with the time? Well, the time, there are really 3 time intervals in this problem. There's the amount of time walking to the east, there's the time spent resting, and there's time spent walking towards the west. Distance equals rate times time for the case when the rate is a constant. This becomes useful. Time is equal to distance divided by rate then, or T equals D over R. So my total time is going to be how much time was spent walking east, plus the time that was resting, plus the time spent walking west. Time is distance over rate. So the east distance, 1287 meters. This was the rate, 120 seconds, the 2 minutes of resting, and then the distance going west, and the same rate, 2.5 miles an hour, is 1.117 meters per second. So we come up with the sum here, 2,136 seconds. And again, you should pause the video. Check this out on your calculator. Average speed is total distance divided by total time. I come up with 1.05 meters per second. I don't have a good feeling in my mind for meters per second. So I'm going to change this to miles per hour. There's a handy conversion factor, somewhat handy. 1.05 meters per second multiplied by the conversion factor of 1 mile per hour is 0.447 meters per second. The meters per second here will cancel the meters per second over here. We'll be left with miles per hour. And it comes up with 2.4 miles per hour. Why would I say this is an acceptable answer? Well, remember, this person was walking at 2.5 miles per hour, first to the east, then to the west, with a little resting time in between. That resting time has lowered the average speed below 2.5 miles per hour. So 2.4 miles per hour is a reasonable number. Now, average velocity. We need something different here. We don't need total distance. Instead, we need displacement. Displacement, we pay attention to reversed motion for this particular problem, but we have a direction and a distance from the starting point to the ending point. That's our displacement. So you can see what's going to happen here. We've got a positive number towards the east, and there's going to be a negative number as we travel towards the west. And the displacement is just the distance, and the direction will still be east for this opposing types of motion, east versus west. Well, let's do this. The distance from the start, we know we traveled 1287 meters to the east. We know we traveled 965.4 meters towards the west. Those are the numbers coming from the miles that were given, that the person walked. So the net here is 321.6 meters, 321.6. And this has a direction. The displacement has magnitude and direction. So the magnitude is the distance, 321.6 meters, and the direction is east. We've not returned back to our starting point, and on this side we'd be west, but our direction is towards the east. So there's our displacement. The total time is the same as the time we use for the average speed. So our average velocity, we divide these numbers and we get 0.151 meters per second to the east, considerably slower than the average speed. If I go back one slide for you, or two slides, the average speed was 1.05 meters per second. Now we're coming up with the magnitude of the average velocity is 0.151 meters per second, and it has a direction of towards the east because our ending point is east of our starting point. It's smaller than the average speed, so it's reasonable. The magnitude of the average velocity will usually be smaller than the magnitude of the average speed for problems where there's some XY motion, both X direction and Y direction. When will the average speed be the same as the magnitude of the average velocity? And that situation would be when we're just moving in a straight line and not doubling back, not going backwards here, but just going from the starting point over to this just east motion. If we'd calculate the average speed here and we calculate the average velocity just on the eastward part of the motion, we'll get the same number for the magnitude of the average velocity and the speed number. So keep that in mind. Usually the speed number is, the average speed number is going to be larger than the average velocity number. Well, other example problems worked out and YouTube videos you can view. They're annotated. They're in lists, annotated in my website, gpclements.com. All the content here is free. You can't resell it, but you're allowed to view it for free. There's no registration. I don't ask for your name. I don't ask for your email address or anything else. And my website does not put cookies onto your computer. So glad you're starting to work sample problems in physics. Ask your instructor if you have any questions.